morning and thank you for coming. My name is Burley. I'm Vice President of Sales and Engineering here at Kaiser. I have a little presentation called Making the Connection. That's not about trying to find dates. It's actually about what type of tooling interfaces are out there in the world today and the differences. What is it that everybody's talking about, and try to better educate you as far as what we know. What are the differences between an HSK, what is big plus, how does it work? How did we get from standard CAT tooling to using Capco, for example, and some of these variations. So this is basically what I'm going to try to talk about is some of the common industry standards that are out there today. When you buy a machine, you're really kind of told by the machine dealer or the manufacturer, this is what the machine comes equipped with. And that's been the basis of the engineering group, that machine tool manufacturer, to figure out and calculate for what their machine is capable of doing to give you the best interface for that model machine. Now, some machines may come with different options. Some may say, okay, you get this with CAT, you can get it also with Big Plus, and you can get it with HSK, and you can get it with KM, and you can get it with any flavor you want. But in general, they're going to say, this is what we have in stock. You know, kind of when you go to the car dealer and they say, you know, this is what I want. And you tell them, well, I want this color. And they say, well, we don't have that color, or we do have that color, but it doesn't have all the options you want on it. In the real world, it's kind of like that with machine tools. You're going to get what's in stock, what can I get in 3 weeks or in a month. And a lot of machine tool companies know what's popular, and they'll stock the machines around it. But it doesn't mean that you can't specify what's going to be best for your working world. If you think that I want to run higher speeds and I want a better connection to what's coming on a standard machine, this will give you some insight to that. So what are the different industry standards out there? And you know, some of the things that you have to be wary of is buying a machine that's equipped with a standard that nobody has tooling for. So there's a lot of, say, HSK standards out there that might be the absolute panacea type solution for this machine, but nobody makes standard tool holders for it. You have to be a little bit careful on that. So make sure that what you're getting is an industry standard. We're going to look at the accuracy, rigidity, damping, dynamic stiffness ratios of all the different connections, how clamping forces might affect different interfaces, and for all the purchasing guys out there, costs. Certainly, different higher technology systems are going to cost more than lower technology. And I've got a little bit of information on that to try to show what those comparisons look like. All that data is without guarantee, by the way. What are the common standards we have today? A little bit of a history lesson. Everybody knows the CAT standard in the United States. This is a US standard only. Nobody in Europe or Japan uses it. It's the most common. It's about 80 to 90% of all tools sold in the United States use the CAT standard. Its baseline was from 1978. It was adopted by ANSI under Caterpillar Tractor. Developed this standard in conjunction with many of the machine tool companies that they bought many of the machines from, and said, this is the way it's going to be. We're going to make it this way. So ANSI adopted it as the D550. Now the granddaddy of the CAT would be the NMTB. It's a 3.5-inch taper per foot, and that's what the old NMTB was based off, and that's where the CAT came in with just the tool chain. Otherwise, it looks identical. The most common sizes are the CAT 40 and the CAT 50. The CAT 30 is non-existent. Although it is a standard, there's almost no companies that make a machine that support it. The CAT 60 also doesn't make the list because there's maybe less than 1 or 2% of all machines made in the world that use a CAT 60 tool anymore. The BT flange is common to Asia. We jokingly refer to it because I can't find a better name for BT than bonsai taper. Don't know what it really means, but that's really what it is for BT. And it's identical to the CAT. The same diameter, same rate of taper, it's all the same. The only difference is the automatic tool change. The tool change V groove is a little thicker. You might be able to handle a little bit heavier tools but the design itself and the symmetry is a little bit better than the CAT tool. So a lot of companies actually like the BT standard for even the United States because it is a slightly better design. It doesn't have some of the restrictions behind the tool chamber like the CAT does. So it's about 10-15% of the market over here in the United States. It's not a bad selection to use a BT30 or BT40. There is a commonality to it. You can buy tool holders for it fairly easily. But the BT50 is a little bit out of range for the United States market. Not many tooling companies stock a good supply of varieties of tool holders. If you're buying BT50 with metrics and things that you can get out of Japan or Asia, it's a beautiful way to go. This was actually adopted even before Caterpillar got going in 1969. It's an MAS 403. So it's one of the oldest standards we've had in the world. Which leads me into the big plus, which is an extension of what the CAT and the BT are capable of. It's a dual contact, a dual fit system built into a standard CAT or BT tool shank system. It's a standard BT or CAT or dual contact with Big Plus. Completely interchangeable from one to the other. I can take Big Plus tools and go into a standard CAT spindle. I can take BT tools and go into a Big Plus spindle. It's completely universal. And there's a little bit of confusion in the market about our patent on that, which is Big DAISHOWA-Americas in 1992 developed the system. And that patent is going to expire at the end of the year. This is not the first company that brought to the market a dual contact steep taper tool system. Ingersoll had it back in the 50s, IBAGs had it even before that for real small tapers. The concept of dual contact technology is not new, and Big DAISHOWA did not patent that concept, although it fits in to the idea. To better explain how Big Plus works is the following. Let's look at a standard CAT 50 spindle. Here you see it over here, you got your bearings, you got your tension system, your inside spindle taper. This will be a little blow-up section of what we're going to talk about right here. Under a normal spindle made to the general specification, the taper gauge line is at the face of the spindle. The tolerance of that gauge line can flow plus or minus 8 thousandths. There's no degree of precision to it. Because when I put a tool into it, I always expect a gap. In most CAT 50 tools, you see about an 1/8 of an inch. So that precision is just not needed. There's nothing contact. It's an open tolerance. Now let's make it into a Big Plus spindle. The idea of Big Plus spindles is we want to maintain that interchangeability from CAT to Big Plus. We want to be able to buy a Big Plus spindle and still use our standard CAT D-line tool holders. I don't want to have to buy only Big Plus. What the machine tool builders or the license from Big DAISHOWA have got is the ability to extend out that face. We extend it down half the normal distance from between the flange of the tool holder and where the spindle was, about 60 thousandths. Otherwise, the gauge line is still in the same place. We don't move that forward either. That stays as it was before. We've only added material to the very end of the spindle. Here's where it gets a little bit more complex. We have to precisely gauge that location. Just like any other dual contact tool, we have to know that when I put a tool into that spindle, I can locate on the taper and on the face. That's a precision to contact face location requirement. So it has to be precisely ground into position. These gauges are supplied by Big DAISHOWA and all machine tool builders throughout the world making Big Plus spindles. To date, that's over 100 builders that are licensed. Or see as an example, because we're working with them this week, they are all Big Plus spindle designs. Every machine that they produce is ground with these types of gauges, Big Plus. These tolerances are held to less than 5 microns in general. how does this now look with my standard Cat 50 tool holder going back into it? Same as before, but we'll notice that the distance between the taper flange face and the spindle face is now only 60 thousandths. So it's working exactly as it would have before. I've not changed anything except the gap that I have between the tool holder and the spindle face. Otherwise, it's identical. And most users who buy and have Big Plus spindles don't realize they're actually working off a Big Plus spindle themselves.
What year did they start that at Maury?
Maury Siki started grinding all their spindles with the N series, which would have been, I think, around 2004. Just check my history on that. Now let's put a Big Plus tool holder in there. The flange of the tool holder is now 60 thousandths thicker than normal. And it also has been precision ground for the taper and the face location together. Before I clamp, what have I established? Taper contact. The basis for every dual contact system is establishing the taper contact fit first. Whether it be Big Plus, HSK, Capco, they all have to fit onto the taper first. Without that, the system will not work. So in a normal Big Plus spindle to a Big Plus tool holder, we will see before clamping at least a clearance of 4/10 or 10 microns, up to normally 20 microns or 8/10. And some machines might even be as much as 30 microns. Generally, this is where we see it. Now, when I clamp this retention system with a 50 tape, it's about 4,000 pounds, a lot of pressure. Every machine throughout the ages has always had an elastic. When I clamp a tool, it's going to pull itself back in a little further. These spindle bearings and everything have an elastic limit to them. They move under this pressure. That's a known, repeatable amount. Every machine does it. So when I clamp, I elastically deform within the limits of normal elastic deformation. And now I bring the tool up that last 8/10 and I get my face contact. But I don't lose the taper contact. That is an extremely important part of the dual contact system. Establishing a taper contact fit first.
What happens if there's dirt on that flange and you still have enough taper engagement because now the dirt's standing between you and the spindle face?
You would have nearly the same problem. The question was, what happens if I put some contaminants on the face of that spindle? The answer is that I'm under very close tolerances. And that contamination will interfere with my fits, and it will make a problem. So it's very important in any dual contact system, whether it be Big Plus or HSK or Capco, that you maintain the fit very accurately. So you have to try to maintain the cleanliness a little bit more than maybe you're used to. But the same problem could exist even if you put contaminant inside the tape.
Well, if you get inside.
It could also interfere.
Easier on the flange.
It is easier, and what Maury Siki does, for example, and I should clarify that, they grind all their spindles for Big Plus, so they're ready for Big Plus tool holders. But as an option, when you buy that machine, they're going to add or install an air blow system to the face. So as the tools change, there's an air blow going across and down the spindle to maintain the cleanliness. We also sell tools that can automatically clean the spindle face if you're getting into a precision area. Or let's say you're going to use 3 tools Big Plus and the other 80 are standard Cat 50. Those precision fit tool holders you can clean first automatically before you put the tool contact in. Unlike HSK or Capco, everything's tool contact. So they all get a face contact all the time. This is what the Big Plus spindle would look like without a tool. The face is in precision ground. Here's your drive keys. These are coolant nozzles. Disregard those. But inside that inner diameter, that's where the normal gauge line is. On a normal spindle, that face would be at that same plane. So that's how you identify if you have a big plus round spindle. The tool holder is the same. It looks almost like a normal, but this flange thickness is thicker than what would normally be, about 60 thousandths thicker. And then it's precision ground to the taper so that we get those precision fits every time. Worldwide, this standard has been in practice for the most part, 20 years. And it's working successfully with thousands of tools and thousands of spindles everywhere. So it's not a new standard. What are the common sizes for big plus in our market? We just talked about the US market. The BBT or BT30 is very common. It's a small drill mill taper spindle. So mill roller drills, for example, I think Marcy's got a new one that they're offering. They all have 30 taper. It's an extremely effective design for small 30 taper machines. It can bring milling operations to these machines that you otherwise couldn't do before without dual contact. The smaller the taper, the more critical the requirement for dual contact becomes. BT44 is available, CAT40 is available, CAT50 is available, BT50 is available, but it's more common to Asian markets only, just like the standard BT50. You can also buy big plus for turning. So if you buy a mill turn, multi-axis mill turn center, you can actually get it with something other than Appler or HSK. Some of the NT machines offered by Maury are offered with a big plus 50. The idea there is that if most of your operations are milling on a mill turn center, you don't have to subject yourself to only turning type tool interfaces. Like Appler, which is more for turning, you can actually put a standard CAT50 spindle and use big plus for your turning operations. Moving over to HSK. It's been around for many years, developed in Germany by Aachen University as a pin standard. It looks very similar to the CAM, which I'll talk about soon, but it's a hollow taper. There's a very small cross section between the taper and the inside clamping. The clamping fingers go inside the tool to pull it into the spindle. To look at this HSK in more detail, let's look at the forms and the sizes. When you hear somebody talk about HSK 63, the 63 refers to a flange diameter. Always. Never changes when you look at that number. HSK 40, flange diameter is 40. Don't worry about any of this, it always refers to the size of the flange. The A is the most common. Probably 80% of all tool holders sold in the United States. As the drive keys down here in the taper, they're not quite as symmetric as you can see. They also have a hole inside the taper that's for manually clamping. If you have a tool that you want to manually clamp for whatever reason, that's what the access hole is for. It has a position for a chip reader. It has the V groove for your tool changer. It has all these other cutouts and a provision for pulling tubes to be put into it. Form C, so if I call out HSK 63C, is identical from this point forward to the A. But it doesn't have the V groove, so it's a manual tool change only. So you're going to see this on transfer lines or even on modular tools. Common sizes for the A and C are 32, 40, 50, 60, 63, 80, 100, 125. But it can go as high as 160. E and F are nearly identical to the A in that the only thing that's changed is this is a high-speed bearing. There are no symmetry issues. There are no drive keys, no positioning location pins, nothing like that. So the taper is doing all your driving. It's a Christian fit only if you're driving the tool. It's not designed to have any drive keys or drive elements whatsoever. It's the first choice for your high-speed machines. So you're going to see this more on smaller machines, 5-axis machines with a high spindle drive. And also in the aerospace market, they go into the form F. And here you see the taper, the flange ratio is a little bit larger than what you see on the Form E. So they designed it around the F because they want a different ratio between the bearings and the spindle ID. Otherwise, it's an identical tool. If I look at the Form E, the sizes are the same as the Form A. Any questions? Can you get in that? Very popular. We sell quite well with the unit. Unfortunately, the Forms B and D, which were a revision for cooling through the flange, never took off. Very, very few machines are offering the Form B or D interfaces. So anybody that's looking at a machine that might be taking Form B should study very carefully the tool selection that's out there before you do something. The latest to come to the market is the Form T. Now with 5-axis and mill turns, the varieties of tool interfaces that you get was also solved by HSK as the Form T. The Form T is identical to the Form A. The only difference is that this drive key has been made more precise, not just in the tool holder, but also in the spindle. So if you buy, say, a 5-axis machine, and it has the Z-axis where you can turn, it's important to ask the machine tool builder, does your spindle support HSK Form T? Which means that the spindle itself is also made to a higher drive key tolerance, and not just the tool. This is important because we have to maintain that center line height. During tool change, I want to make sure that the center line doesn't deviate. So the precision drive keys are what allow us to keep that. But you can also counter this by using the V-axis of the machine and tilting it 45 degrees, placing the insert at 0. In this way, no matter how I turn the tool, with any variations of the drive key, I can maintain perfect center line height. So there are ways around it, but it's a little more complex. That's the HSK Form T. CAPCO is also an ISO standard. It was adopted as a standard in 2007, but it's a very complex tool to produce. It's a polygon shape, which requires perfect fit 360 degrees around that polygon profile. The taper itself is a 1 in 20, and it's got the face contact. The size, C5, C6, C8, is all relative again to the flange diameter. It is also clamped with an internal clamping mechanism, just like HSK, but the wall section of the CAPCO is much stiffer. So it does have a higher bending strength than, say, HSK. KM is also a standard. One standard, the other one standard, they're nearly the same standard number, just one off. Looks nearly the same as HSK. Clamps a little bit differently in that you have balls which engage into the taper and then into the spindle to pull it in. So it's a little bit more complex in that you don't have a clamping system running inside to clamp the tool like you do HSK. Otherwise, it's similar dimensions. This wall section is nearly the same as an HSK. One in 10 taper. So don't confuse with HSK between wood. So how do we define the differences? What makes the critical choices for you? Accuracy, axial and radial. Rigidity, what is its stiffness and static? What is its damping capabilities? What is its dynamic stiffness? What is its vibration? And lastly would be the cost. If we take any machine tool and we turn up the spindle to high speed, the spindle tries to grow, tries to move outward, produces full force. No phenomenon, you can't change it, it won't go away. The only way you can counter it is with a dual contact system. It won't allow the tool to pull in farther due to that opening. So as I clamp the tool, I open up the speed, open up the spindle, the tool wants to come in farther. With dual contact, I eliminate that possibility. Here's an example with big plus versus conventional to illustrate that. At 5,000 RPM, the dual contact and the standard Cat 40 behave nearly the same. There's almost no deformation due to high speed. As I start ramping up the speed to 15,000 RPM, dual contact prevents the tool from pulling in deeper. Whereas the conventional tool, taper contact only, is going to keep drawing itself in deeper and deeper. And you're going to lose as much as 1/1000th of an inch on your Z-axis height. So when you're trying to profile at high speeds, you see that you're not able to control depth. This is the reason for it. You're not able to control your reliability. So we like to say low to moderate speed, cat 40, cat 50, no problems. And that would be up to around 10,000 RPM. Over 10,000 RPM, dual contact is almost required. So that's the axial accuracy that we talked about. It would be the same if I was looking at HSK or Capital, which we don't always say is a high-speed system. Then we go to the radial accuracy. What kind of radial accuracy are you trying to achieve? We took tests at DAISHOWA-Americas in Japan with a standard machine Big Plus 40 taper, checking it between Big Plus and BT 50 times. We tool changed in and out of the spindle to find out what the accuracy is. With the Big Plus, we had less than 1 micron variation over 50 tool changes. The reason for that high accuracy is with that phase contact, when you pull a tool in, there's no guarantee that the tool is being pulled directly back. There might be some lateral forces engaging on the spindle and the retention system, which tries to force a conventional tool to get one way or another. So over time, you will all of a sudden see spikes in your repeatability. And the reason for that is you take your contact, it's just not accurate enough compared to dual contact. So in radial accuracy, when you're trying to really get below 10 microns, dual contact is where to go. Over that, you have pretty good reliability with taper contact only. But again, rigidity. To illustrate HSK, you have a tool there with a spindle and a clamping system. How does that work? When I hydraulically actuate the internal pull rod, it sends this wedge into contact with the tool holder right here. That clamps it all the way around. So it's an internal expanding clamping system. So for high speed, it works very well in favor of increasing the clamping force as the spindle speeds grow. Comparing it now to a steep taper tool holder, we have an external clamping system, which is working against high speed. So as high speed goes up, clamping fingers have to work that much harder to retain the tool in position. But when we look at the rigidity, the contact area, or taper contact area, HSK is very short. When we take away the drive keys, and just look at where is it contacting the spindle, it's a very small area. Whereas the Big Plus or standard spindle taper tooling has a wider, longer length of taper engagement. Now we have to look at the retention forces. And the reason I bring this out is some companies say, well, we have the highest retention force band system out there. That's a portion of the whole system. You shouldn't just structure yourself saying, just because it's high, it must be better. Well, they are different, and these are traditional values for Big Plus or cap. And the Big Plus spindles have no higher clamping force than conventional. We don't put amplifiers on them. But the HSK does have, I look at 63 compared to 40, higher clamping force. It's capable of higher clamping force the way it works. HSK 100 to Cat 50 is a higher clamping force. Capco, depending on whether or not you put their patented gas cylinders into them, can be even higher than the HSK. Let's compare them to the shape again. If I look at a 100 millimeter 4-inch diameter tool like HSK 100, the length of taper engagement is very short. The face contact areas are the same. But again, the taper contact is much wider. Static stiffness is primarily dependent on the diameter of the face for all systems, which true natively. It's ultimately going to depend on the reload, how much time force we put onto it as far as the rigidity.
Question.
Yes, sir.
That last line, the HSK, how come it's only part of the taper that's engaged?
The drive keys of the spindle are released, so if I look at my spindle, it's released back here. There's no taper contact in the spindle from that point forward. These drive keys and all that, if you look at the spindle, if I was drawing that in there, you'd see it's cleared out here. Okay? So we just look at stiffening a Cat 40 spindle, going from big plus to a traditional Cat 40. What are the results? What can we expect? Just by adding that face contact surface, I can increase the loads and reduce the deflection on the tool itself without changing the clamping force. So it's important to have face contact for the higher rigidity. What does this mean?
I have a question. If you have machines with both big plus spindle and conventional spindle, and you're using big plus tool holders, can you use them in both? And is there any?
Yes, you can use them in both convention. You can use a big plus tool into a conventional spindle, but you won't get the effects of the dual contact. And you can use a conventional tool holder into a big plus spindle, but you won't get the advantages of the dual contact. Only a big plus spindle with a big plus tool gives you the dual contact. If I can reduce my cutter deflection, I can produce more accurate parts. My presets will be closer to the final part. So the actual rigidity as a bending moment also has to be looked at. When we look at these diagrams, we've all seen them out there in different trade magazines one way or another. HSK, Big Plus, and Capco, they all have a different diagram. And it is dependent, again, on the preload, how much time we force to put in each system. The Cat, or Big Plus, is in this teal color. If that's teal, I'm not sure. The HSK is this one. And the Capco is this one. So these are your bending moments. This is how much force you can take before it tries to topple out of the spindle. And what we mean by toppling is where we lose that face contact. Look at the knee of the diagram. That's the critical point. Where does it start to rapidly move forward? And on the HSK, you see a huge change here. And that knee is influenced by not just force, but by the length of the tool. So the longer the tool becomes, the wider the force needs to be to topple. And it's the same with any of these tools. The longer length of engagement here, and the thicker cross-section in here, allows it to maintain higher static stiffness inside the spindle. Static stiffness, all that matters if you never go over the spindle. So if you're turning, this is all you have to concern yourself with. So let's go to the more complex area, and that's dynamic stiffness. Now when we start turning the spindle, we have vibration, we have frequency. The system, the tool holder, the machine, cutting edge, all interact to create a natural frequency. And this has been going through a lot of study over the last 10 years, but it's dependent on the frequency. Every machine, every interface is different. So if I take a Morisiki with an HSK spindle and a Morisiki of the same machine class and size, put a big plus into it, these frequency diagrams are going to be different. So I can't just say this machine is always the same no matter what interface. These stability lobe diagrams tell you at what speeds do I get stable cutting. The green zones are my stable cutting. The chatter zones are, of course, areas to stay away from. If I never go over depth of cut, in this case, 100 thousandths, I'll always be stable at every speed. If I go to 200 thousandths, I have to watch this area. At 5,000 RPM, I can get chatter. If I move over to the next speed, maybe 6,000 or 7,000 RPM, I'm out of the chatter. These lobes change, again, depending on what interface we put into the machine. How do you do that? Besides other companies doing it for you, you can buy these mobile tap testing equipment. It's got a calibrated hammer, which you don't want to break your tool when you hit it, but it's got a little accelerometer based on it. And when you tap the tool, it feeds back to this laptop computer, and gives you analyzed data for the frequency of that system, for that tool, for that machine, for that interface, for that clamping force. These frequencies are measured, generated through this computer program, analyzed, and a stability load diagram for that work center is developed. You know, companies like Blue Swarf and others are developing online statistics that you can put in any cutter size for your machine or a Cat 40 spindle or an HSK 63, and it'll tell you where these stability loads fit without actually measuring. When I get these stability loads, and you look at them on programming jobs, and easily and predictable machining result because I'm not putting myself in the tab zones. This is generally just for the milling operations. You'll see that what we look at as a tooling interface is the higher frequency is a stiffer system. The lower frequency is the less stiffer system. We want the highest possible frequency you get. You want these loads as tight as possible. So what happens when we make the system stiffer? Increasing the stiffness shifts the frequency response of the sweet spot. It's going to move up and to the right. So we're going to be able to increase our depth of cut, and we're going to be able to go to higher speed. So the area shaded in black would be the weaker system. The area in red is the stiffer system. Say we went from a Cat 40 to a Big Plus. So I can run to higher depths of cut at a higher speed. These are my improvements. This is where I can improve my cutting efficiency. What if we make it weaker? Counterintuitive, what you think you want to do, it actually can be to a benefit to make it weaker by going to, say, a longer tool. So I reduce my dynamic stiffness, and I see in black the areas that this system, the weaker system, is better than the stiffer system. So it's not always one direction. Any questions on that? So that brings us to the cost. So you've analyzed all this, run through all the math, the college professor will be proud of you, and you come down to the very bottom, you start putting off your bids for different quotations. Looking at industry-wide, reputable, quality-made tooling, these would be the predictable costs associated with, say, a 30-piece roller package on a Cat 40. Collet chucks, milling chucks, and then holders, stone holders. Somewhere about $5,000 to $8,000 would be about what you pay. If I was to tool it exclusively Big Plus, as a general rule, depending on where you buy your tools from, because you can buy them not just from Big Kaiser, but also from Sandvik and Rio Fix. They're also licensed companies. So you can get competitive offers from around the industry to get different pricing and different varieties, but it's about 35% more. They're exclusively tool. In the case of Big Plus and Cat 40, though, I can select the lower demanding operations to use standard Cat tools, and the higher demanding tools to use Big Plus in mix and match. Although it's not our first recommendation, it can be done. That's the way the system was designed, and it can be used. And it is used in practice by many customers throughout the country. If I tool on the same machine with HSK 63, the varieties and the complexities go up, the costs also do. And every tool has to be HSK, so it's a little bit more expensive, and with Capdo, even more. The cost goes just a little bit more up because of the complexity of producing Capdo, the variety and number of companies that compete for it. So about, looking from here to here, some very big differences. But what is your return on investment? How much more productivity do I get from here to here? That's a small difference in the tool up. Over the life of that machine, which might be 3 to 7 years, that small difference is not going to be paid back. It's going to be gone in 1 month. So you need to look at the higher productivity solutions from the beginning. Looking at a 50 taper, the results are nearly identical. A little bit higher in cost of the Big Plus compared to what's standard non-Big Plus tools, but a little bit less than a total HSK program and a little bit less than the capital. So this would play into, again, mill turn machine with Capto, mill turn machine with HSK, or mill turn machine with Big Plus. They're all available for that interface. What are my conclusions for today? Be competitive in the global market, which you all are. You have to look at every detail of every piece of equipment you put in. You need to look at taper phase contact systems as a way to become more globally competitive. Big Plus can be justified across the whole range. Low range, high range, high speed to low speed. Ultra high speed to HSK is preferable, especially on the smaller machines. Traditional taper contact tooling is going to result in status quo. If you want to buy a new machine, if you want to change something in the tooling, don't expect too many changes on the result.
What speed would you consider ultra high speed?
Over, for say a 40 taper machine, I would say over 20,000 RPM. 18,000 RPM, if you're looking at 25 or 30,000 RPM, spin over 40 taper, over 20,000. Big Plus again is justified up to about 20,000 for no problems. Capability, your spindle interface should be equal or more than the machine tool itself. You don't want the machine tool spindle, which is relatively low cost part of the equation, to be the result that brings the level down. So don't go down in the quality of your spindle interface. Go up. Don't let it be the determining factor for how fast you can run your machine. And then what you hold your tool with, your cutting tool, should also be more than what the interface is capable of. You don't want to put a weak tool holding system into a tool contact. For example, buying a HSK tool holder, 100, very expensive machine, and holding your tool to a side lock and holders. That would be the weak link in that case. That's our presentation this morning. If there are any questions? Yes, sir.
How would you say that this business with the Big Plus 40 compared to the standard 50?
There's been statements out there that if I take a 40 taper machine with Big Plus, I can get nearly the same performance of a 50. In certain cutting conditions, I would agree to that statement, but overall, you'll never be able to take a 40 taper machine and equal the cutting capacity and torque, moments, lengths of what a 50 taper can do. So if I know my tools are short and I'm looking to optimize, getting down to a 40 taper machine instead of a 50, I can do that. But if my tools have to be longer, heavier, and I really want to put a maximum torque to the cut, I gotta go to the 50 taper. It would not be able to, that face contact is not going to be the cure-all to moving a 40 taper machine into a 50 taper class, in general. I wish we could say that, but it's really not.
It looks like a lot of the fifth axis machines coming with 40 taper.
Yeah.
As opposed to 50.
Yeah, there's very few. I mean, the larger spindle interfaces are going to be HSK in that case. Great. Thanks for coming again. And I'll be around if there's any more questions.